Okay, yeah, no problem. And he's not around. Yeah, I know. I got this incredible screw up.
Okay, welcome to our CMU seminar series. Today we are delighted to have Dr. James Kempf here. Let me briefly introduce him. He graduated from University of Arizona with a PhD in systems engineering in 1984 and immediately went to work in Silicon Valley. Prior to his current position, Dr. Kempf spent 3 years at HP, 13 years at Sun Microsystems, primarily in research, and then 8 years at Docomo Labs USA as a research fellow. And then he worked for 10 years at IETF, was chair of 3 working groups involved in developing standards for the mobile and wireless internet, and was a member of the Internet Architecture Board for 2 years. He is the author of many technical papers and 3 books, the latest of which, titled Wireless Internet Security, Architecture and Protocols, was published by Cambridge University Press in 2008. Since 2008, Dr. Kempf has worked at Ericsson Research in Silicon Valley on software-defined networking, OpenFlow, and cloud computing projects. So we are really delighted to have you here and looking forward to it.
Okay, thank you. Am I on the mic? Yes, I think I am. Okay, good. All right, so what I'm going to talk today is about some work we've been doing at Ericsson Research on how to get basically a telephone operator to innovate like Google. And by that I mean innovate in a way that's fast and gets results quickly. This is an outline. First of all, I'm going to talk about the problem. Then I'm going to have one slide about the historical perspective. Then I want to talk about what we think the platform has to be for this, and it's based on a bunch of different technology trends that have been developing over the last like 8 years. A brief one slide about the process, about what the process needs to be. I mean, we've mostly worked on the platform because we're not a telephone operator, and so we don't do research in processes. If we were, we probably would have that as part of our research program. But we do have some ideas what might be useful. And then I want to talk about 2 prototypes. The first one is Cloud Atlas, and that stands for Cloud Accessible Transport Layer System. And the second one is about network slices. And then I'll just briefly summarize, and we'll have a slide on the credits about who was involved, because as Martin said when he was at HP, software engineering is a team sport. And I thoroughly believe that. So no one does anything alone. So anyway. So how does service development work in an operator today? Well, basically what happens is you're given this platform, which is a collection of protocols and systems that have accumulated over like 50 years or more. And it's just concerned with user-facing actions like call control and billing. And the typical process is a group of maybe 30 people. It takes 1 to 2 years of effort and many millions of dollars, even perhaps tens of millions, depending on the complexity of the service. And a lot of the effort is put into ensuring the underlying hooks are there and programming them, if not. And the basic bottom line is it's very time-consuming and expensive. So this isn't the way most internet companies work, obviously. So as a historical perspective, the industry, like the telecommunication industry, has spent over 15 years working on APIs for communication services. The Parlay chain, one API, the latest is one API. So the question is, where are all the applications? I mean, you'd think there would be a lot of applications coming out of this. Well, oops, sorry. The problem is there's a collection of interrelated problems here about the way these standardization efforts work. And in fact, one of the problems is they were run as a standardization effort rather than to get people actually implementing things. Initially, the APIs exposed maximal information. So you get to see everything. There was no abstraction there. So they were too complicated for enterprise IT folks to basically use. And APIs were primarily concerned with control of communications. So what you also need is you need the ability to automate deployment and configuration and, in fact, cross-domain orchestration. So these APIs were primarily focused on wired telephony service. And you really need to be able to go across mobiles, the wide area network, and the cloud. And of course, when they were developed, there was no cloud. And be able to kind of orchestrate all of these into one thing. And so that's one service. And so that was lacking. And they also supported, they didn't support, the APIs have to support maximal automation. They didn't put that into these APIs. So if you have anything less than that, what you do is you increase the amount of OpEx and you lengthen out the deployment cycle, and you get things to be too complicated. It just makes it more expensive and more complicated. And finally, and most importantly, the APIs have to involve out of use cases. If you sit around in a room and talk about this stuff and then come up with some APIs and spend like 5 years doing it, you're not going to have anything that people can use. Well, you might, but it's unlikely. So what you need to do is you have to support use cases, because that's where you get the idea about abstractions. And in fact, the key to having a successful cross-domain orchestration platform is simple usable abstractions and maximally automated deployment. Those are the two things you need to have. Because if you don't have the abstractions, programmers have to spend a lot of time understanding the APIs and the side effects of all the parameters and all the configuration. And if the configuration and deployment isn't automated, then the people that actually deploy the system take a long time, and you end up getting the same sorts of problems in terms of that. So this has been the problem historically with communication APIs. So taking a page from the internet companies, what you need for Agile service deployment is a platform and a process that supports it. It has to be engineered for fast innovation. It has to be easily enhanced for new use cases. It has to be built on existing technology when that's good enough, so you shouldn't need new technology for it. It should be stable enough for a long term, and it should cover cross-domain, because the network has multiple domains. That's what the platform needs to be. The process has to be flexible and adaptable to fast-evolving customer tastes. It has to be low overhead, and it doesn't require CS PhDs to run. And you should be able to turn around new features set in weeks rather than years, right? So these are the two parts of Agile service development. And the part I'm primarily going to talk about, like I said, is the platform, but I'll have a couple of words to say on the process. So what about the platform? Well, the first aspect of the platform is SDN, and I'm sure everybody here is familiar with that. Basically, it started with OpenFlow, and OpenFlow allows a simple TCAN-based forwarding from a centralized controller. But the problem is most networking devices don't have the hardware to support TCAN-based forwarding at line speed. There are some promising approaches out there, but I mean the hardware that's out there doesn't do this. So that's basically a problem. So what happened about 3 years ago is SDN got generalized, or OpenFlow got generalized to SDN. So the SDN has 4 basic properties: a centralized control plane, direct control of the forwarding elements from a controller, and applications which are built on the controller northbound API, and a real-time network management. So these are all the sort of, so in other words, the last point is integrating network management together with control plane, so you have real-time network management. So that's what I'm saying in the last point there. You combine the network management and the control plane into a single controller. So what happens in an SDN network is that the northbound API then becomes a platform for transport and network management control. So this is the first piece of doing cross-domain orchestration and being able to let service providers innovate better. An example of a representative OpenFlow controller is OpenDaylight, which is open source. Their hydrogen release was in January or late January. It has OpenFlow on the southbound here. Let's see, I don't see where it's at. Oh, there it is over here. It also has other protocols like netconf, BCPE. So basically, you can do abstraction of control plane and the separation between control and data plane using something like OpenDaylight. So this is an example. So the next technology trend is cloud computing, and again, I'm sure everybody's familiar with this. Basically, the infrastructure as a service APIs allow you to virtualize and automate server storage and network deployment and configuration. The platform of a service APIs allow you to virtualize application deployment, although PaaS right now is in a very early stage in terms of communication applications. The infrastructure as a service part is somewhat further along, even though it's going to require some work to really make it support NFV applications, but nevertheless. And finally, the orchestration platforms allow you to support complex service deployment. So these are all aspects, and most of this stuff is open source. Cloud Foundry is open source. OpenStack Heat is the OpenStack orchestration engine. So the third piece of this is service-oriented architecture. Now, this is nothing new to people in the enterprise software space. Essentially, what we need to do is apply service-oriented architectures to the telco applications. The idea behind SOA is you structure the service in the center as a collection of self-contained components. And these components make the business, basically make the business logic stateless, and you put the state into the database. And then the front end is the client. I mean, this is really something that people do nowadays just by part of the good software practice when you're doing enterprise applications. The important point, though, is that the components communicate through well-defined APIs, mainly HTTP, remote procedure call, REST APIs, and they don't actually expose the internal part of the application to their client. So they act as a kind of a module that's well-defined that people can compose in various different ways. And that lets you basically change the insides of it if you have to support new sorts of networking equipment. So in the case of network APIs, for business logic, it would be some business logic change. But that's the basic idea. And this allows you to take the components and combine them into services. So this is one of the driving patterns behind NFV. So at a high level, what NFV is about applying all of these pieces that I was talking about to telecommunications applications, but specifically at the level of a particular network domain. So taking functions like IMS, which gives you basically internet telephony, or the mobile core for handling mobile devices, and virtualizing them, putting them on top of a virtualized platform, using SDN for control and management of the networks if it's available, and then applying service-oriented architecture to the components, defining service APIs, arbitrarily composing them, and in fact, maybe even dividing these big chunks of functionality into smaller chunks along the lines of the 3GPP functional architecture, and then defining the APIs between them. The difference, though, is that unlike enterprise applications, telco applications have state. And in particular, they have connection state and mobile tunnel state. And you can't actually put this in a database because a lot of times you have to consult that state on every packet, or almost every packet. So it's really not an option to do that. So this is going to require a somewhat different approach than what's done in SOA. Okay, so this is a cross-domain architecture we came up for orchestrating across multiple service provider domains. Over here you have the different domains: RAN, the radio network, fixed residential access, and fixed enterprise access. And you have the access network here, and you have, on this side, you have the cloud. So you have cloud orchestration. You have the VNF managers are controlling where, they're part of orchestration, or controlling where the different virtual network functions are deployed. You have SDN, which is controlling the routing. And then you have an OSS system, which is setting up services, and then cross-domain orchestration on particular parts of the network. And then you have cross-domain orchestration, which is actually orchestrating the different components to set up a service. And in some cases, this should be doable by the customer. So it should be possible, and I'll talk about a case, one of the prototypes we did where we actually did something like that. You should for example, have a customer portal, and then, for example, suppose if you wanted to choose a wireless plan that's got, instead of has a certain size of data, and you wanted to actually choose with that the ability to get enhanced QoS on certain video applications that run in the cloud, right? So this would be a way to be able to do that and have the operator be able to set up a portal. They could set that up using the APIs that were exposed on this cross-domain orchestration. Right, so what's missing? Well, probably a lot. I mean, we did a couple prototypes, like I said, and actually 3, but there's a lot of stuff that needs to be done here that we didn't actually look at, like, for example, policy, service, billing, and charging. In the last 6 months, I've been looking at charging in the cloud, and the way we've done that, you could actually do cross-domain charging, but it's just very preliminary work. Security and identity management, other BSS functions. Being able to do network management monitoring. If you actually have SLAs and you're giving people enhanced QoS, you have to make sure that they're getting that because they're paying for it. And all of these will be reflected in the northbound APIs that go across the cross-orchestration layer. Some of them will be, some of the SDN functionality and functionality from other parts, like the mobile network, will be constricted so that only certain parts of the API show, because the key is to finding the usable abstractions, the ones that provide 90% of the functionality with 10% of the complexity. That's really important because that's the way developers can do stuff quickly, is that they can take and be able to do something that is very quick and it solves 90% of the cases. If you have to actually go down and get that last 10%, somehow that last 10%, or more of the complexity, then you actually basically have to go and figure it out, and it might take longer. So, and of course, you need to pay for that. The customer has to pay for that. All right, so a little bit about process. I didn't talk a lot about process, but basically, you want to have, you follow the Agile principles of software development. So these are good software engineering practices. Do code reviews, modularization, all those good things that, that people learn about, and that people do in good software engineering projects. Don't use a lot of global variables, all that kind of stuff. So the other thing that actually has come up in the last few years is this thing called DevOps, or continuous development and deployment. This can reduce the time until new features are put in. So you essentially cut down on the number of features. So instead of having a release like twice a year or 3 times a year, you have a release on a monthly basis. You only release the top 10 features or maybe less. And you integrate the development and operations, so you're continuously rolling out. And you also incorporate testing so that you have proactive destructive fault testing. This is what Netflix does. They have something called the Chaos Monkey that kills various VMs and sees what happened and then fixes up if there's any problem. They're able to then control how the system reacts to fault conditions. So that's important. It also reduces the amount of effort you have to put into doing your network management system, because if you have this sort of generalized system in there, then you can actually respond to things more quickly and fix. Okay, so what about prototypes? Well, the first prototype, like I said, is called Cloud Atlas, and basically what this was about, this was an attempt to kind of not exactly eat the dog food, but kind of like maybe the dog biscuit or something. It's just to try out this idea with an example of a cross-domain application. So this is basically an outline of what the abstractions and the applications are. It's basically elastic WAN networking with SLAs for OpenStack. And we did a tight integration between the Neutron data center virtual networking, which people used to call Quantum, but now they call it Neutron, together with WAN virtual networking, and that in this case means MPLS. And you could also use it for IP. In fact, we did in the one prototype a little bit later with IPsec VPN. So the idea is to use a VPN in the WAN, use virtual networking in the cloud, and that's the way it works. And so these are the abstractions, and they mirror to a certain extent the Neutron abstractions. So at the very top level, we have sites, which are essentially just places where there's availability of Cloud Atlas service. We have gateways which provide that service. They have a particular API on them. And we have a VPN, which is an instance of the service, which customers are able to very quickly get up a VPN. So the idea is that you can have, just like in the cloud, where you can bring up a neutron network, without any, in a couple of seconds. The idea is that you can do the same thing in the wide area network. You can bring up a VPN quickly. You can connect it up to your cloud network, and you can use it. And we have virtual links and virtual ports. So we designed a very simple customer usable API based on these abstractions. And we also have abstractions for bandwidth. And the idea is to reduce the operator management overhead. So these are some of the applications that we have talked about. Disaster recovery, remote backup and replication. This is one of the ones we showed. Enterprise voice over IP in the cloud, and streaming video with SLA. So these are all things one could do. And I'll show you an instance of this one. And there's another one that we have that we did, which is setting up a VPN from a branch office using a portal. I'll talk about that a little bit. And the last thing is it's independent of the WAN VPN hardware and software technology. So you can use it with MPLS VPNs, layer 2, layer 3, IPsec VPNs, whatever you want to do. We've also thought about how to use it with layer 1 VPNs on top of optical. That's also possible. We didn't do any work in that. Right. Okay, so this is the architecture. So basically you have the two sites, and you have they're running OpenStack, and you have gateway, which goes to the WAN. And the sites are running a cloud operating system, generically, or OpenStack in our particular case. You have an orchestration layer, which is orchestrating across the sites. And you have network virtualization in each of the two sites that's virtualizing the data center. And then what we add is this Elastic Networking Manager. So the EN Manager talks to the orchestration layer. It orchestrates the setup of the virtual network, the end-to-end virtual network between the two sites, and specifically between VMs in the two sites. And then in each site, there's a Elastic Networking agent, and there's a plugin that then talks to the gateway. So the plugin deals with the details of the hardware. That's how we get the abstraction, is we abstract details into the plugin. Similarly, the plugin here, in the Elastic Network Manager, deals with the complexities of talking to the two operating systems. Cloud Atlas has a public API, which people use to set up the VPNs and the end-to-end slices and connectivity. And then the management API that goes between the Elastic Networking agent and the manager to allow the manager to communicate with the agents. What we did in a later version of this, which I'm not going to talk about, actually it's the one we did in the second prototype that I'll show you. We got rid of the Elastic Networking Manager, and we got rid of the agents, and we only use the manager. So the manager then talks to the gateways. And we now have an API that we introduced into OpenStack, which is we're trying to get this standardized as part of OpenStack, and it's called the Gateway API. And that takes care of a lot of the management API. So before we didn't know kind of what the API would be here, so now we have that. Do that if we can get them to standardize. Okay, so the first application we did was bandwidth calendaring. So the idea behind bandwidth calendaring is you have a piece of bandwidth, a chunk of bandwidth, and you get it at a certain time. You pay for it only while it's active, and during that time you can use it for whatever you want. Well, in fact, what we did use it for is to do checkpointing. What checkpointing is you take a VM and you migrate it to a different data center, but you don't actually start it up when it gets over there. So it's like live migration, except it's not live. It can be used for like backups, or for example, if you want to do disaster recovery, those are two example applications. If the one data center goes down, you can instantly start it up on the other one, and then it works. And of course, the state will be somewhat out of date, but If the application is stateless, that shouldn't be a problem, provided the database is migrated as well. So this is the idea. So the operator can essentially sell his capacity during the night when there's very little traffic, and the data centers can then sync, or they can actually do it during the day if they want to make sure to use it for disaster recovery. So this is basically that. This is a modified version of the OpenStack dashboard, where you can see where we put in the Elastic Network control. So the other one was a joint project we did with T-Mobile. Actually, they just showed this a couple weeks ago in Berlin, and it's basically with what we call VPN to go. The idea here is that you have a gateway, essentially a portal where a customer goes in this case Adidas, who happens to be a customer of T-Mobile, and you check that they want to set up a VPN from branch office, and then they have to provide some authentication information, and after that it goes ahead and deploys it. In this case, we have Magdeburg, which is a city in Germany, and Frankfurt, and this is a branch office. The branch office will wants to get the VPN, and so they ask for it, and it comes up. It connects in through basically what it does is it downloads a VM to the branch office that then runs the gateway on that side. And the only thing that isn't automated yet is the deployment of the IP addresses on the VPN on the clients. And we're talking about how to do that. I mean, one way to do it would be to put them in DHCP and then invalidate everybody's lease, and then have them have to go back and re-authenticate to get the, re-get the, not authenticate, but get a new lease. But that seems a little bit extreme. So there should be some easier way to do that. But right now we don't have that quite in there yet. But, the other thing this has is so this connection between the branch office and the data center is a GRE IPsec tunnel. So that's essentially one tenant, which is just the branch office, in this case Adidas, and the connection between the data centers is basically virtualized. It's running VLAN tags, and it's multi-tenant, so multiple tenants could have connectivity in both data centers to be able to use them. Now these, in the actual demo, this was in Berlin. This one I think was in San Jose at our office and Ericsson's office, and this one was in Mountain View at T-Mobile's office. How it might work. This is basically IPsec with GRE, and so it just goes across, and then there's a stitching function. That's what the Gateway API does. It stitches together the neutron network together with the VLAN. You could also do it with MPLS too. We've done both ways. Okay, so that is the Elastic Cloud Atlas Elastic WAN prototype. The other prototype we did is something called network slices, and actually it's very similar. We're doing end-to-end slices of the network. In this case, though, between the mobile network and the cloud. And what we use this for is on-demand policy-driven TOS, so you can use this for mobile enterprise cloud services. So the idea is that you could have an enterprise can have a policy that they implement that specifies that certain applications in the cloud get specialized treatment. Perhaps you have high-definition video and you want specialized treatment. HD video doesn't go very well over mobile networks unless you have specialized treatment. And then the operator sets up a portal so that the enterprise can actually go in and configure enhanced QoS. So this is an example of the fast deployment example. After the operator sets up the portal, there's no involvement of the operator at all. It's all taken care of by automation. I have a little video here. This is Martin Shearling, who some of you probably know, which demonstrates how this works. And if we have everything set up correctly.
This network slices demo illustrate answers to 3 questions. How can operators package and present the network towards enterprises? How can operators differentiate mining cloud and mobile capabilities? And how can operators radically increase the setup time of new services? In the lower panel, we see the dashboard that the enterprise uses to dynamically control the network capabilities to use. The enterprise can connect the service, in this case a real-time video service, to a network package that the operator offers. We call it a network slice. The network slice contains a mobile network piece, a cloud piece, which has a compute and a storage component. And also there is a dynamic price point with the current settings of the network slice. Here we see how video traffic flows from the end user through the mobile network to a video server. And we have two, one deployed in the cloud and one in the operating cloud. The blue box is the cross-domain controller that combines mobile network and cloud resources to create the dynamic slice dashboard below. Let's look at the end user value. This is a field service engineer out monitoring equipment using high-quality video over LTE. The field service enterprise is not happy with the video quality. So let's go in and dynamically upgrade the cloud from internet cloud to the operating cloud. The price point changes, and here we see the quality improvement.
No audio?
What happened was that we steered the traffic to the operating cloud server, thereby avoiding the latency towards the internet cloud.
Okay.
This really shows the value of the operating cloud. Now, there are still some quality issues because we have put simulated background traffic on the mobile network. So the enterprise can go in and upgrade also the mobile network piece of the slice to an optimized network. The price point changes, and now the video traffic is carried with another policy across LTE and the mobile packet. Here we have a high quality, low latency upstream video using a dynamic control network slice.
Our field service engineer looking at his drone. Yeah, so this is our slices. And the next one I've got is this architecture. Now, essentially what this is you can see here how it's set up. This is the EPG, which is the EPC, the Evolved Packet Core Gateway out to the internet or to the external network. And SAPC is Ericsson's version of the PCRF, the Policy Control Function. And one thing we did with the PCRF is we packaged it as an SOA service. So it includes charging, and it has an SOA API. So there's a REST API on here, an LDAP, and so you can actually get in. You can get in and you can actually talk to this, and they talk about abstractions like flows and sort of prioritizations, QoS based on the 5 tuple, the 3GPP 5 tuple, and those sorts of things. But SAPC has actually no idea about mobile video cloud services. Absolutely no idea. And so up here we have the orchestrator. So there's the dashboard server is something that the operator uses to set up the orchestrator. The orchestrator is what the enterprise admin uses to talk to basically set up the prioritization for which applications get enhanced QoS in the mobile network. And down here we have OpenStack. We have Compute, Nova, the Neutron networking, and storage, Cinder, or whatever storage option you want to use. That's kind of standard. And then there's a gateway in the cloud, and then we put a policy extension on this, which notices when the user starts up an application that is tagged as having enhanced QoS, the cloud gateway will notice the IP address, and it'll tell the orchestrator. The orchestrator will go back and it'll call SAPC through these APIs. SAPC will set it up, and the EPC will put it onto an enhanced bearer. We'll move it from default to an enhanced bearer. So that's basically how it works, and it's an example of what you can do with this sort of architecture. It took about maybe 6 months to do this, and yeah. So, okay, summary. historically, the telco service deployment has been really slow and costly, and really applying this sort of internet internet company approach to doing services is what is needed. So there's all these new trends like SDN and cloud and SOA, which actually isn't so new, but it is certainly new for the telco services. And applying these sort of technologies to telco services, I think, is the key. And really, you have to find usable abstractions at high complexity, package them as a service, and then deploy them in a virtualized platform. If that service happens to involve routing, you can use SDN. So that's the basic idea. And I haven't talked much about requirements, but the basic requirement is agility. That's the thing that operators want, and I think this is the way to do it. So we actually sort of ate our own dog biscuit, and we said, well, okay, so let's try this out, and we did it on a couple of examples. It took us about 6 months to do the network slices demo. It took us about 3 months to do the branch office part of the VPN to go demo, and about another 3 months to do the inner data center part. So it's an idea of how you can actually quickly do services if you have the right sorts of abstractions and you have the right pieces that you can put together in kind of a Lego-like fashion. So, and here's who was involved. So Rasha, Stefan, and I at Ericsson, and also Olaf Beckman and Vlad, who you saw in the video, Martin Shearling, Victor McClellan, who's no longer at Ericsson, he's now the CTO of Singtel, and Srini and Anarund at T-Mobile, working on the VPN to go. That's it. Questions?
Oh, any questions?
What breaks, from your perspective, if you try to migrate things, not just the operator cloud, but all the way down into
It depends on what the application is. I mean, there are clearly things where you might get some benefit. For example, with CDN, I think that's something where definitely you get some benefit. But I think you'd have to look at it on a case-by-case basis. I don't know what specifically what would be involved. Another thing I might think of is if you think about how to do augmented reality applications. If you have a lot of data involved in those, it might make sense to put that down, especially if the data is like localized. You might want to, like, for example, let's suppose you were doing something. Let's suppose you were going to take all of the San Francisco Bay Area and talk about, do things about what sort of plant communities were there and the plants that were in those and where those plants were. I mean, there'd be like thousands of. So you might want to actually, instead of putting it in some gigantic database somewhere, you might want to actually cache it down in the RAN. And I don't know what would break on that. I think it would require like looking at the particular application.
Well, I think CDN is kind of an easy one because the latency doesn't matter once you start streaming the socket.
Right.
For AR, there's a round-trip latency to the terminal.
Mm-hmm.
The challenge application is, let's imagine that you and I are playing real-time first-player shooter game, and so the person-to-person latency
Right.
across two different terminals, maybe at different parts on the RAN server that currently is on the other side of the core,
Right.
where the latency is just tolerable. The
Yeah.
question is, how closely can you bring the game server
Right.
to the two?
So I did a little bit of work on this at Docomo when I was. I actually wasn't looking at games, but at Second Life, and I think one of the problems is when you can move some of the interaction closer to the user in the RAN, but the thing is, if you're talking to someone who's not in that particular cell, or if the RAN is controlling multiple cells, then you don't get any benefit from reducing the latency, and so you end up. I mean, in a lot of cases in Second Life, you end up talking to people in like England or Germany or something, and so you end up not getting as much benefit from that. But if you're actually working, if you have a bunch of people who are playing a game locally and it's involving a lot of real-time interaction, like first-person shooters or something, then I think you would get some.
Question from online. Have you performed any performance measurements?
Okay, so this is something that we've talked about, but part of the problem, so if, and this is actually is a difficult problem with getting this kind of work published, because people that want to see performance measurements or something like that, if you think, let's think about the way object-oriented programming was in the early 90s, and I happened to be around then. So what happened was that people thought that, well, you know, there's a better way to structure programs, and that is using object-oriented programming. So they basically coupled function calls together with state, and they called it an object. And there were a lot of papers written about the right way to do that, and there wasn't any performance measurements done because the point of the paper wasn't about performance. It was about how to structure the program in a way that made it easier for people to program. Now, I would say, oh, okay. So I would say that that's what we're doing here. So basically, we're talking about abstractions. I mean, Scott Schenker has a very good video where he talks about abstractions. Most of the work we're doing is done on top of existing networking protocols and existing networking equipment. So really, all you're going to see is the same kind of performance that those equipment and protocols give. In some cases, like for example, VPN to go, typically for an operator it takes months or weeks to set up a VPN. In this case, you could set it up in a couple of minutes. That's one thing the operators don't want to talk about. So we can't publish that kind of stuff. They don't like to. I mean, and some operators actually do have elastic VPN, and like Verizon has elastic VPN. So, but anyway, that's the idea. Okay. Other questions? Yep.
Thank you so much, Dan. Is there any other questions? Okay.
Thank you.
So much. So we have refreshments outside. Please enjoy.